Discussed in grade 11, you discussed endo and exothermic reactions. And what is this graph an example of? Endo or exo? Exo. How do you see that? The energy, so this is the energy of the products is less than the energy of the reactants. That means that it gave away some of this energy to its environment. Okay, so it heats up the environment because energy equals temperature or heat or thermal energy. Alright, so this is an example of an exothermic reaction, and we can see it. I show you this reaction in class on whenever. Yes?
I gave you the notes with the pages. Didn't I give it to you?
I think the active extras. Then it's probably in ma'am's class. Het jy extras op hoor? Nee man, maar seker mos dit nooit as op Let's make notes on, rather do it in your writing book. Do you have a writing book here? Make notes in your writing book. Okay. Okay, so I showed you this on, I want to say Friday. Yes, it was Friday, where we had zinc and we let it react with hydrochloric acid, and it gave you a salt. Now you couldn't see the salt because it was dissolved in the water of here. So that aqueous stands for surrounded by water. So you have the hydrochloric acid that is surrounded by water. So that So that salt there is aqueous because it's dissolved in that same water, because it's all happening in one beaker, right? And then it gave you off, or it gave off hydrogen gas, and you saw that that fizzling, and I sent it around and you could feel that it heats up. So this is an example of an exothermic reaction, and the way we show it is we say the heat of the reaction, so that stands for the heat of the reaction, is smaller than 0. So how do you calculate that heat of the reaction again? It's the energy of the reagents minus the energy of the products. No, other way around, sorry. Energy of the products minus the energy of the reagents. So if we look at this reaction, let's say the energy of the reagents was, let's make it 100, and then the energy of the products is less than that, let's say 30, if this is our 0 mark. Then to calculate the heat of the reaction, it will be the energy of the products minus the energy of the reagents, which will be 30 minus 100, and you get negative 70. And the fact that it is negative 70 tells you that it released energy into the environment. So there you can see that it is smaller than 0. Okay, then I want to know, what do you call this part of the graph? What do you call that part of the graph? It has two names. The part where you go from where the energy of the reagents was, and then until it reaches that top part. What do you call that going up? The definition for that is the minimum amount of energy for a reaction to take place. What is that? Activation energy. So the name there is the activation energy. So the symbol for that is an E with a capital A. It also has another name. Its other name is dissociation energy. So the energy needed to break the bonds, to break the things apart. Then we have something here at the top that we normally write in square brackets. I would write zinc ions, chlorine ions, hydrogen ions in brackets like that, there at the top. What do you call this thing where you have broken up all the bonds and now they are like in the ion, very unstable phase? Activated complex. The activated complex is there at the top. And then the particles rearrange, they get together, they form bonds. they become more stable, they release the energy. What do we call this energy that they give off, that they release? Oh my goodness, now I see the activation energy. It's just the yellow. What do you call the energy that they release when bonds are formed? That's your clue. When bonds are formed. Bonding energy. Bonding energy. It's the energy that is given off when bonds are formed. Alright, and then this part here, the difference between the energy of the products and the energy of the reagents, that is your heat of your reaction. Okay, now it looks like you sort of remember something about this graph, which is good. Now we are going to do another type of graph in this chapter, so don't get confused between the two graphs. Okay, this is a graph that shows the potential energy. This must actually, Access must actually read the potential energy in kilojoules per mole. Potential energy versus, they'll say, the course of the reaction or the time or something like that. And you get exo and endothermic. What would an endothermic graph look like? Say again? The products will be greater than the reagents. Okay, so you end higher. And let's say for this endothermic reaction, I want to add a catalyst. What does a catalyst do again? A positive catalyst. It speeds up the rate of the reaction without taking part of it itself or without changing anything. So what it does is it lowers the activation energy. It lowers the activation energy. So you don't go up as high. So that is where you add a catalyst. Okay, any questions? Okay, so when we did the practicals on Friday, we looked at how many different things? We looked at, I think we said 5 different things that influences the rate of a reaction. Can you remember some of them? When we did the practical, I said, if you compare this with this, which one will take place faster? Well, what was this and this? I had powder versus granules, right? And the powder reacted faster. You remember that? We had a higher concentration and a lower concentration. The higher concentration reacted faster. We had a reaction where we put in a glowing splint, where we added a catalyst. So a catalyst will make it go faster. And then there were 2 other things that I didn't show you, but I spoke about it. I did show the one thing, but not practically. I said the type of substances you use, vinegar versus sulfuric acid. Which one will take place faster? Sulfuric acid. And the other one was heat. If you heat up something, it will take place faster. If you wanted to make tea, okay, and you put the tea bag in boiling water and cold water, when will the tea dissolve faster? Boiling water. Alright, so the other one was heat. So we are going to look at 5 things for the rate of the reaction. So keep that at the back of your mind, this whole chapter. Alright, then I'm going to read and then explain. It says there, reaction kinetics. Okay, let's just stop. What does the word kinetic refer to? Kinetic refers to movement. Think of kinetic energy, movement. Okay, right. So, reaction kinetics, reaction motion. Chemical reactions do not all progress at the same rate. Okay, meaning they don't take place at the same rate. At equal speeds. Ne? Some takes very slow, some takes very long. And the way we can think about that is if you have if a ship wrecks at the ocean, right? So a ship goes into rocks or sand, or whatever, and it's stuck there. Then over years, it will start to rust and degrade, and maybe after 200 years, the boat will be completely gone. But if you take potassium and you also a metal, and you put it in water, whoosh, there it goes. Right? So both are metals, both react with water, but it happens at different speeds. Okay, now it says there, reaction rates are not constant, only an average rates are meaningful. Okay, so we're going to look at average rates because at the beginning, the things happen fast and then it slows down as the concentration or the amount are used up. Okay, then we get two types of reactions. We get homogeneous reactions and heterogeneous reactions. What does the word homo refer to? Don't say gay. The same. Okay, homo means the same, hetero means different or opposite. Okay, so a homogeneous reaction is where the reactions and products are all in the same phase. And most of the time that is gases, gas. For example, if you had nitrogen gas reacts with hydrogen gas to give you ammonia gas. That is a homogeneous reaction. Then a heterogeneous reaction is when they are in different phases. When you have different phases, for example, when you have magnesium solid, so like a magnesium strip, and it reacts with oxygen gas and it gives you magnesium oxide solid, a white powder. So they are in different phases, so that's a heterogeneous reaction. Okay, then you are going to calculate the rate of reactions. Okay, from graphs mostly. Now, when I told you in grade 10, when you hear the word rate, what must you think of? Divided by? Time. So the rate is always, as you can see here, divided by time. Okay, always. Then the definition here, and they do ask this definition quite a bit. Okay, how do you define the rate of a reaction? It's the change in concentration, and remember the symbol for change in is that delta. And what is that again? It's the final minus initial. So the change in the concentration, or it can be the change in mass, or the change in volume, or the change in mole. Okay, it can be any one of those things. It depends on what information was given to you. So the change in concentration or mass or volume mole of reactants or products, again, it depends. Are they giving you information regarding the reactions or the products? Per unit time. So you're not going to say per second, you're going to say per unit time, because some reactions, like I've just explained, a boat rusting in the water, your unit time will be years. And for potassium in water, it will be seconds. Okay, so unit time will be what is appropriate in this thing that we are busy with. Okay, then here, excuse me, you can see I give you a lot of different formulas. They are not all on your data sheet. Okay, I actually wonder, is it on your data sheet at all? For a moment, I'm thinking it is not. It is not on your data sheet. Yes. But I don't know if I have a... No, it's grade 12. Okay, so not on your data sheet. So you must remember this. But what did I tell you? I told you just, and you told me actually, when you hear the word rate, you think of divided by time. So you know that. And then you're going to look at what was given to me in the graph. Was it moles? Was it mass? Was it... Or they'll ask in the question. Determine... The question will be determine the rate, and then they'll say in moles per minute. They'll tell you that. So then you must know I must take moles and divide it by the minutes. Okay, so they'll give it to you like this. So then moles over minutes, it will be this reaction. Okay, so you're going to write down rate is the change in mole, the change in time. And here I tell you now mole per seconds, but it can also be minutes or hours or years or whatever. Okay, then you can see here, ma'am, why are you giving us so many formulas? I tell you, this is how you calculate the rate when you are given the reactants, and this is how you calculate when you're given the products. And if you look quickly, they look the same, but there's a small difference. The small difference is the negative there in front. Okay, so I I said here at the top for you that when you calculate rate, the answer must always be positive. So when you do a calculation, you quickly calculate rate and you get a negative answer, then the only thing you're going to do is you're going to sneakily put a negative into your formula and a negative in your substitution, and then you're going to get a positive answer. Okay, so you can do that, right? But your answer must always, always, always be positive. Okay, because you can't go back in time. Okay, but we will practice using these formulas in lesson 2. Okay, now, how do we calculate? Not calculate, determine the rate of reactions. Like, physically, if I was busy with a practical, what would I do? Now, there's different ways in which you can calculate the rate. The first one here that I show you a picture of is the downward displacement of water. Now, you actually had to do this in grade 9 as a practical. Did you do it? Yes? No? What school did you go to, Krutron? Shuna! No. You maybe had a dream about that, but I think if I give Shuna this picture, she won't know what's happening. I think she could have given you a part of this, but not the whole thing. But I think she maybe did do a part of it. Okay. So interesting. Okay, listen carefully. It's almost like the practical that we did, but it just continues. So here's a zinc and a hydrochloric acid, and when it reacts, we saw a gas, or we heard a gas coming off. So what you would do is you put a stopper in there with a tube. It can be a glass tube or a plastic tube or whatever in there, so it captures the air that is given off. And then the air travels through here, and what you have on this side is a water bath. It's just a bucket with water in it. And then you fill the test tube full of the water, the same water, and then you bring it upside down like this. So you can bring it out of the water, just not out of the water, but just until that part is almost out of the water. Okay. And you let the delivery tube go into that, and then it will, as the gas is formed here, it goes through here, and then it goes up, and it will push this water down. And what you can do, you get test tubes that are marked in centimeters, and then you can measure, or read how much gas is formed here. Did you do it?
Yes.
Okay, but can you guys imagine it? Yes. Okay, so this thing is called the downward displacement of water. Can you think what's happening here? The water is being pushed down, the downward displacement of water. So then you can see, all right, I can determine the volume of gas that is formed. So if we want to calculate the rate of the reaction, we would say, right, after 1 second, how much gas is formed? 2 seconds, how much? 3 seconds, how much? 4 seconds, how much? All right. Okay, so this is called the downward displacement of water. Did you write that down? Downward displacement of water. Okay, right, so this is one way in which you can determine the rate of gases. So it says here, gases, the mass of the gas can be determined by measuring the mass of loss of reaction mixture. So that means you can put here, you can put a scale and measure the scale readings in certain time intervals. Okay, and if you can have what is the loss in mass here, you know what is the gain in mass there. Okay, because this is a closed system. Can you see it's closed? The gas cannot escape. Right? Or you can determine the volume of the gas by collecting it in a gas syringe over water as indicated. So this is here. Okay. Another way in which you can collect or measure the rate of the reaction is if you have ions. Okay, so if you know it's going to form something with a positive or a negative or whatever. I'm going to read in the next page. If ions are used or formed during a reaction, electrical conductivity serves as an indication for the concentration at different times. So then you'll put in, we're going to have a chapter similar like this later on, where you're going to put in electrodes in liquid, and then you're going to have an ammeter or voltmeter or whatever, and then you're going to measure the rate of the current. Okay, and why can we determine the rate of the current? Because ions are, like example, silver ion is something that can conduct electricity because there's a free electron roaming around. Right, the next one is color. Now this is not that easy or accurate actually. If you look at color, it says color change can be a measure of can be measured accurately by a please pronounce that word. Photometer. Would you say photometer? Why don't you say thermometer? Why you say thermometer? So it's not photometer. Anyway, so you get a certain appliance where it measures the brightness or the concentration of a certain color. Okay, but I do not have an example of that thing in the lab. Okay, and that can be used as an indication of the concentration. So this meter measures the concentration of a color over time. Or you can look at a precipitate. Now, what in the word is a precipitate? Yes or no? Say again? No. We say that in geography, but in science class, a precipitate is an insoluble salt. Insoluble salt means it cannot be dissolved in water. So it forms something like you can, in your head, you can think of paint. The paint that they use to paint tar roads with, yellow and white and red, so you can't drive. You don't want those lines to dissolve in water. Right? So that is actually a precipitate that forms in a certain reaction. It was a chapter that was taken out due to COVID. So unfortunately you missed that whole chapter in grade 10. But we actually made precipitates previous years. So you have reactions where a certain insoluble salt is almost like a very like tough powder that forms. And you can, okay, I'm going to read. The relationship between the transparency and the concentration of the precipitate can be established. So you will see it will, I actually want to do that practical with you. We'll do it once in the class, where we're going to form a yellow precipitate. And it stinks a bit because there's sulfur in it. But we're going to add things together, and then you'll see it forms, the liquid will start to become like murky. And then it will be very yellow, and then it will be so yellow you can't even see through the water. And then after a while, you'll see the yellow goes down, down, down. It will form like a yellow paste at the bottom that you can get out and dry and have yellow paint to paint with. Okay. Yes.
Why did it take so many chapters out due to COVID, and why haven't we put it back? No, I'm saying 11 too, but...
So the years was shortened in COVID, right? So we didn't have time. So they took out the chapters that was not that important to build on. And then I don't know why they haven't put it back. All right. Okay, let's look at how we're going to use those calculations. It said there, 50 grams of zinc granules is added to 500 cubic centimeters hydrochloric acid with a concentration of so much. Assume that the zinc is completely covered by the hydrochloric acid, so nothing is sticking out that cannot react. The balanced equation for this reaction is, okay, so there again, so this comes from a grade 12 question paper. Okay, so this is what you can expect. And we did this practical. That's why I wanted to do those few practicals with you in class, because you saw this happen. Okay, now before I'm going to read here, I'm just going to look at my graph. Because remember, graphs are your friend. You can visually see what's happening. Okay, let's look at the graph. Time, concentration of hydrochloric acid. Okay, so there's nothing regarding the zinc on here. Okay, then if I look here, I see my zinc, that's concentration, right? Not my zinc. My hydrochloric acid starts with 2 mole, this is just 2 concentration, and then it ends with 0.77 after a while. Is the hydrochloric acid used up? No, you have still left over. Okay. So it means this one was in limiting reagent? Zinc is our limiting reagent. Okay? Then number 2, when was the reaction completed? At 45 seconds. How do you know that? The line is horizontal. Nothing is happening. This is a question that asks you in a test. Which one is the limiting reagent? Obviously zinc, because there's hydrochloric acid left over. When, at what time interval did the reaction stop? 45 seconds. Then my last question. When was the rate of the reaction the fastest? Is it between 0 and 15 seconds, 15 and 30 seconds, 30 and 45 seconds? When was the rate of the reaction the fastest? What do you say, Rory? Okay, but I don't want to do 3 calculations. This is like a 1-mark question. Visually, from looking at the graph, when did the reaction take place the fastest? Okay? What did Laura say? She said you must do that calculation because that calculation gave you the rate. Okay, now let's quickly look at just the formula. I'm not going to do any calculation. For that formula, the rate is the change in concentration for this one specifically over the change in time. What did we basically do here? We looked at the change in the y-axis over the change in the x-axis. That is our gradient. So the rate is your gradient. Okay? So what I want you to do visually is look at when is the gradient the steepest. Obviously, at the beginning. Can you see that? Why? Why is the gradient the steepest? Why is the reaction going the fastest in those seconds? Think. You have this beaker, you have the zinc, you add it, finish. Why is it going like this at the beginning and then it slows down?
Because that's the amount of product.
The amount, not the amount of product, the amount of reagents. You have lots of hydrochloric acid, you have lots of zinc, everything is in full concentration, it's a perfect amount, but as it reacts, it becomes less and less and less. So think if you zoom now into the particles in your head, zoom in. At the beginning, you had a lot of particles that can bond with one another. Then after a while, there's like these random particles that are looking for something to react with because all the others are already taken. Alright, are you with me? Okay. So just from looking at the graph, I can get a lot of information. Right, now let's look at the question. They say, write down 2 observations for this reaction. Observation is something that you can see, feel, or smell. Okay, so you're not going to tell me hydrogen gas forms. Okay, technically you can tell that. But you didn't see the hydrogen. You just saw gas forms. Now you can be clever and say it's hydrogen gas, okay? But you're not going to say the product is hydrogen. That's basically what I wanted to say. You can't say the product is hydrogen. You must say I saw gas form, which is hydrogen gas. Okay, so that is one observation. I'm going to just split my page in 2. One observation is gas, specifically hydrogen gas formed. What was the other observation that you saw in this reaction or experienced? I sent it around in class. You felt it became warm. So you say beaker heats up, or you can say it gives off heat, or you can say it gets warmer. But for example, you're not going to say it's an exothermic reaction. Okay, that's a conclusion. Because it heats up, it's an exothermic reaction. But what did you observe? All right, then the next question they ask you there, calculate the average reaction rate for this reaction over 45 seconds. Okay, so they say over 45 seconds, it's meaning from the start to the finish. Okay, so they didn't ask just for one section. Okay, so the rate here we see is going to be the change in concentration, because that is what we have on our y-axis, over the change in time. And change means final minus initial. So we have 0.77 minus 2 over 45 minus 0. Please fill in that 0. I think last year or 2 years ago, they deducted marks if you didn't fill in that 0. Don't ask me why, but they did. Okay, and you got a negative answer, right? Negative 2.733 times 10 to the power negative 2, or 0.027. Yes? Okay. Now, two things. Number one, we got a negative answer. Not allowed to have a negative answer. So what am I going to do? I'm going to put a negative in there, and a negative in there, and then there will be a positive. So I'm just going to put brackets around there. So I know it's negative times this whole business. And the last thing is I must have a unit. What is my unit going to be? What was there at the top? It is moles per decimeters cubed. So I'm going to say moles per decimeters cubed. And then what was there? It's time. And we divide it by time. So it is seconds minus 1. All right. Okay. Grade 12. Ma'am will give you homework for the weekend. You don't have homework for tomorrow.